The review of the lesson from the 29th of March, Tuesday, where we were primarily looking at convergence, the first of the four challenges. We looked at this way in the beginning a little bit just to understand what convergence is, and now we go into more details. Here is the challenge, and I think the first thing that would be good to do would be to take a look at visually what we mean by convergence in terms of the way that it looks. Seen this a couple of times. The idea is that these seemingly random paths, slowly but surely, one step at a time, converge into a better path. They converge. Convergence really brings everything together, particularly the hardest to explain terms, frankly. So what this is the hover over, just copied and pasted from the main, and without going over it myself, I'll let you read through it and try to put it into context. Maybe read through this now and then watch the video for 20 minutes, whatever it is, and read it at the end, see if it makes any more sense. But basically what this is saying, just generally, it's saying that convergence is making the chromosomes, or the tors in our case, to be more and more similar, more and more better, right? And it's doing so through a bunch of different choices like selection techniques. Are we doing stochastic universal sampling, or are we doing roulette, etc.? The exploitative nature of crossover, the fact that crossovers mix two good parents to get a good or even better F1 generation. And then this I'll talk about shortly, simulated annealing. Also, other exploration strategies of novelty searches and mutations. So basically, combining a bunch of different things that you can throw into a genetic algorithm: selection, crossover, exploration, novelty searches, mutations, throwing all these things into the mix. And this might be a good time actually to go over to this. Throwing these things into the mix, the selection, the crossover, the mutate, a couple other things, to slowly but surely make things that aren't so good to be Yahoo, what we're looking for. And just quickly, this is my attempt of summarizing the whole thing. This is our basic algorithm, right? So initialize 100 random populations of cities or towns around Lakeland. Evaluate, we give them a score, which is simply adding up the distances in kilometers. If we reach the termination condition, we break, which I'm saying do when we reach 993, and Yahoo, there it is, the best. But most iterations we're going to, from the ranked or unranked, depending on the selection technique, we're going to select. And we do need to rank in the case of truncation, and again I'm using truncation as the example just because it's the easiest one. Take the top 50, select. Then with those, they are the breeding generation, they breed with each other, and this is probably being recorded, I'll move that over there, that the P1 and the P2, like we looked at last time, through the exploitative nature of crossover, mixed genes. And this isn't the perfect diagram for PMX, but it's close. And then I'm just throwing in a random mutation there as well. And ultimately, we do output the best. So I'll come back to this as need be. But in terms of convergence, the idea is that as this loops and loops and loops and loops and loops, we're going to converge onto similar, more and more similar routes, which are going to have better and better total kilometers in the case of the traveling salesman problem. Right? So the point, the reason that I went there is that we saw in that diagram mutations. We saw on that diagram crossover. We saw in that diagram selection. And then there are other kind of parts of those that we talk about next. From this most, I was going to say difficult, but I didn't say difficult, this most thick of paragraphs. It's the one just before the challenges. It's got a bunch of stuff that is not defined. So I guess that's going to be my approach right now. In the same way as with this top paragraph, or a bunch of paragraphs, having read it, listen to me now, you should go back 20 minutes later and read it again and see if it makes any more sense. Same thing with this. So again, this is just a whole lot, but here I'm going to go through verbally what each of these things are, and then I'll go through them in the paragraph. So fitness landscape is the whole problem set, or solution set, potential solution set. It's all the different possibilities that could be a solution to your problem, including really non-fit ones in the outer reaches of the fitness landscape. Local extrema, A local extrema is either a local minima or a local maxima that you reach, which causes early convergence. And it's not an absolute optimal, it's just it's an extreme, pretty good result, and because of that, it short circuits the whole process, and you end up with a suboptimal solution. But anyway, so local extrema we want to escape, as you'll see when we bring the sentence all together. Hill climbing approaches are non-heuristic usually, and they just incrementally, step by step, make the solution better. But what happens is they end up at this local extreme. You know what I'm going to do? I'm going to interrupt this for just 1 second. I'm going to show you when we run this genetic algorithm visually what that's going to look like in terms of the reaching an extrema, in this case a local minima, which we're not all that happy with. There's a convergence. It went really quickly, but it happened. See how the average end up converging with the best, and basically the average is the best, and they all just kind of converge, not close to the best that we could probably theoretically get to. So that's where we go and we tweak different things and try to make this genetic algorithm run better. Yeah, so I'll leave it at that. And so back to these definitions. Just getting straight, the difference between exploration and exploitation. Exploration in genetic algorithms means, going to the outer reaches of the fitness landscape, looking at non-fit solutions. And then exploitation is different. It's not exploration and exploitation. They both start with the same 4 or 5 letters, but they're different words. Exploitation is convergence. It's just another word for convergence in this context. Simulated annealing, we'll get back to again. That's basically fine-tuning by not always going the direction that seems best, but trying other directions as well, and you never know what you might come up with. Convergence is convergence. That's what we're going through. Novelty search just means being rewarded for a search that doesn't look like it's yielding something very good, but you never know. And that's the old, I've seen this a few times, that's the old, go with the not very good and a couple of not very goods and see what you come up with, because you never know. Remember that one? We'll get back to it. So, novelty searches. Problem space, you know what, for right now it's kind of the same thing as fitness landscape. And then initial parameters, well, we've got our program here, and there are parameters primarily here that you can change, like the crossover rate and the mutation rate and so on. That's a really big one. It really makes a difference. So parameters in running your algorithm, your program. Selection strategy, we know what that's all about. And crossover operator, we know what that's all about too. And I just will mention quickly that we don't say crossover method, we say crossover operator. So that's just kind of the way it is. Just get used to it. So if I read through this now, let me read through it and add a few words and see if some of it starts to come together for you. We're talking about convergence. We're talking about how we want to have this route, this traveling salesman route, converge to something that's really good. So, and I will read this. The advantages of genetic algorithms are thought to be their ability to simultaneously sample vast fitness landscapes, in other words, sample lots of different solutions, while escaping local extrema, where you just get stuck with something that's good but not really good, that might trap more traditional hill climbing or these non-heuristic approaches. Successful implementation of genetic algorithms strike a natural balance between exploration, where we're going to the outer reaches and trying these non-fit solutions, and exploitation, where we're taking the best of a couple of parents and crossing them over. And many techniques, such as simulated annealing, which can fine-tune the balance as the algorithm progresses towards convergence. So not just exploration and exploitation, not just randomness through selection and crossover, but also other little things like, purposefully going in and saying, let's stop here and explore some good-looking options. More recent research has focused on specific rewarding of novelty. So you reward novelty. Not only do you not run away from it, but you invite it to a certain degree as a means of encouraging algorithms to explore the remote regions of the problem space. And again, just for this context, it's basically the same thing as the fitness landscape. Other design choices and not just design choices, but when you're running it, other design choices such as initial parameters, as we looked at, selection strategy, as we've got 4, and crossover operator, we've got 3. So your selection of your choice of what you're going to use for parameters, and we'll look at this shortly, and which selection strategy you're going to pick. I like the tournament the best. Crossover operator, again, what I think would be best would be to start with the CX and then go to maybe PMX. But anyway, they all influence the performance of the algorithm, although it's generally not possible to predict their effects, so a trial and error approach is usually adopted. So the more you watch, the more you read, the more you think, the more you assimilate this stuff, the more this paragraph's actually going to make sense to you. So like I say, at the end of this video, it would be a good approach to go back and look at either the convergence definition or this and see if it makes a lot more sense to you. I've got a good little summary diagram here, which is basically the written version of this to put convergence into context. All these things by now, hopefully you'll appreciate. Initialize the population, evaluate to give them a score, check to see if you've got a good enough solution, select using one of the 4 selection techniques, cross over the things that have been selected to combine the parents, mutate randomly, but not that much, and by doing so, you will converge one step closer each, or maybe not each and every step, but through the iteration, but generally you're working toward convergence. Then there's the second part of the assessment statement. The first part of the assessment statement is just to understand the role of convergence in genetic algorithms, and it's hard, and I did my best within 10 minutes to put it into focus. And I think you'll be fine, but you need to take more than 10 minutes probably to really fully understand it. And the whole case study, right? The whole case study explains the role of convergence through the different techniques that we're going to use and we've already looked at. So the second part of this is the factors affecting convergence. Well, I mean, they're listed up here, right? And so I've just separated them out and below the list or whatever here. So if you wanted the list is here. We want to both converge and avoid early convergence. And I think you appreciated that this is early convergence because we should have been able to get a little bit lower if we had changed some things like things we're going to look at now. So what are the factors that affect convergence? The selection strategies, the exploratory selection strategies. Which ones should you pick? You shouldn't pick, as far as I'm concerned, truncation. You should pick the other one called, and I've done so well, remember, stochastic universal sampling is the one that I think you should pick, or tournament. Novelty searches, you should introduce them. We haven't seen how to code those, but you can just imagine that there's some sort of a part of your algorithm where it says, okay, stop, and now look around this not so good part of the search space. So novelty searches. Exploitation, repeating now, most of the stuff that I'll probably see from now on is repetition of what's been said in the video previous and in other videos, because we did crossover techniques last class, right? So the factors which affect convergence include exploration, which selection strategies and whether and if you do novelty searches, exploitation, crossover, and the techniques that you have chosen to use, and the crossover rate, the degree to which it is employed. And does this mention? No, somewhere else there's something that goes on with that. Because well, I'll tell you right now, there's a strategy also called Elitism, which says don't cross over the best. For each generation, just take the top 5 or the top 5% or whatever, and just leave them. Don't even cross over them. And that kind of is associated with crossover rate. Simulated annealing, a little bit more to this, including an analogy where you're settling into your seat, and sometimes you move a direction which is less comfortable. But by moving that direction, you've explored the space and realized that it wasn't a good direction to go after all. Sometimes you move into something, you're sitting in a seat in a plane or a movie theater, and you move one direction, it's not too comfortable. And you think, well, actually, if I just put my elbow over here, ooh, actually, that's great. So it makes sense to do this simulated annealing, even though it may seem counterproductive, because you never know. It's one of these random exploratory techniques. And then initial parameters. And this is basically going to wrap it up that population size, obviously, the bigger the population size, the better the chances of success, but it's going to slow down your computer. That's all. The initial routes and tours, one of the things that was interesting that came up in class that I mentioned is that one of the ways to do initial routes is to not do them completely randomly, but rather have a person just sit down with pencil and paper, draw out something that looks like that, connect the dots, and say, okay, start with this and see if you can make it better. But you definitely would want to start with random tours also, so that you explore the fitness landscape to its highest potential. Number of generations to run, I mean, it's going to reach a point, as we can see over here, where it's not going to make any difference, right? But you wouldn't want to have stopped it here. So you'll just know by looking at the graph or whatever way you have of analyzing it that you've run it enough times. So here is elitism. So elitism or not. Elitism is where you just keep a certain, if I use the diagram over here, haven't really used it very much, but you know, here, instead of crossing these three over, you'd cross over the next three, but these three you just leave. You wouldn't even use them. That's elitism. And mutation rate, the rate of mutation, 1% seems to work good in a lot of cases. In the one that we were using, or can use if you want to get into it, that this 0.05 actually is about as good as it gets. So mutation rate is not ever that high. Is there anything else to say here? I mean, obviously, same old obvious stuff, like you wouldn't want to have too much mutation because you're never going to get anywhere. But if you don't have enough, then you're never going to explore those really novel situations. Like, I'll put this up on the screen one more time, that sometimes you can get a not very good with a not very good. Via, you know, both of those could be not very good because of mutations, and coming together, you end up with the great solution. Then there's the other mutation idea here that sometimes this is a different scenario, I know, but sometimes you just need a mutation because there is no other solution. And you know, you might get stuck in a pretty good situation here where everything is just pretty good. Throw in a mutation, you're going to get a bunch that's really awful, perhaps, or not as pretty good, but then you're going to end up with one, and all you need is one, because we're just looking for the one optimal solution that the mutation has made appear. And then the termination condition, you know, if you don't do enough iterations, you're not going to get a good enough result. If you've reached a certain level of fitness, then okay, you're happy. So the termination condition makes a difference also, as does your machine. Like, there's a certain amount of time you're going to run the algorithm. If you have a supercomputer, it might be different than if you have a laptop. So all these things, and they're all in the case study. So if you get a question like this, what things affect convergence, just look through the case study and find this paragraph, you know, and start to show that you know what these things actually mean, particularly the ones that are going to be, well, particularly these things. And I didn't get to this in the class, but there's one last section, but it's been alluded to several times, and that is the problem of early convergence is that we don't want things to become seemingly optimal before they're actually optimal. And how do we know that? We only know that by exploring the fitness landscape as widely as we can. So not the easiest, this to put into perspective and into context, but go back, take a look at those top two paragraphs and see if it makes a little bit more sense to you. And that is convergence.